Oh, hi, welcome. This is chapter 6 lecture. Chapter 6 is on electronic structure of atoms. In chapter 2, or previously, we looked at the models of the atoms, and chapter 6 is all about the electronic structure. Electronic structure is basically how electrons are arranged in an atom. Electronic structure is basically the arrangement of electrons in an atom. Uh, in this chapter, we gonna look at how the quantum theory, right? How quantum theory is used in explaining or explaining the model of an atom as opposed to Bohr's model of an atom, Anne's model of an atom, K.K. Thomson model of an atom, and Dalton's atomic theory. In chapter 6, quantum theory also explains the importance in chemistry and how quantum mechanics explain or describe atoms. This is all what we look at in chapter 6. Now, what is electronic structure of an atom? Electronic structure of an atom refers to the number of electrons in an atom, distribution of electrons around the nucleus. Remember the Ernest Rutherford model of an atom. This is the part of the nuclear model, that in the nucleus we have the protons, and outside the nucleus we have electrons and the energies of those electrons. Allow me to show you, on the periodic table. I think this will be a good opportunity to show you how electrons move around the nucleus. So what you see here is the helium with its 2 electrons moving around the nucleus. And in the nucleus, there are 2 neutrons and 2 protons, right? 2 neutrons and 2 protons. We will see in chapter 6 how these electrons are arranged. For example, in magnesium, we have 12 electrons, right? Moving around the nucleus, 12 protons. This is for a neutral atom. Now, that's what we will look at in chapter 6. As usual, there will be 2 parts. There is part A and part B. There is part A and part B. The first part, part A, we look at the first 34 slides, and then part B from section 12, 6.5. This is the outline, okay? The first part A will cover section 6.1 through 6.4, and part B, section 6.5 to 6.8. Please be making your own notes. You can read on those sections. Make your own notes. You can also download and print a PowerPoint slide so that as I go through, you can also make your own notes. So let's see, in chapter 6, right? Section 6.1, electronic structure. This chapter is all about the electronic structure, and electronic structure is basically the arrangement of electrons and the energy of those electrons, right? Remember the nuclear model, electrons move around the nucleus following what we call orbits, right? And this is the new nucleus where we have the protons and the neutrons. We'll see how the electrons are arranged, all right? Are arranged according to either all right, according to the position on the periodic table. When I look at this, how many electrons? Using the simple excess electron, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is an atom of neon number 10 on the periodic table. So the business, or what we'll be looking at, is how these electrons are arranged. It may seem odd to start by talking about the waves, right? You know the waves, but when it comes to atoms or elements, it's extremely small particle. These will be relevant, and all what I can say about the wave is, first we will look at the wave nature of light, assuming that this is, I got a, I don't know if it's a tennis ball, but nevertheless, if we take this as an atom, right, we need light. If the electrons are in here, we need, it's dark, we need light in order to see the electrons. Likewise, it's just like in a dark room, if you are looking for an object or something in a dark room, you will need to turn on the lights for you to see. For us to really understand and look at the electron around the nucleus for any atom of any element on the periodic table, there is a need to understand light, okay? There is a need to understand light. And it's even beyond that, because beginning 20th century, the way we look at the light, all right, it has really revolutionized how we live. Beginning 20th century, there's been dramatic changes in the way we look at the universe just because of the light. So section 6.1, the wave nature of light. Okay? Light coming from through the window has wave properties. And I will use this illustration, all right, with a purpose. If you look at this, these represent a wave, similar to what you see on the PowerPoint slide. And it has what we call the wavelength, the distance between two adjacent peaks. You see this wavelength. Chemists use this symbol we call lambda, all right? This is lambda, all right? We call this lambda, okay? And it represents wavelength. Distance between two adjacent peaks, all right? This is just distance between two peaks, two adjacent peaks, all right? It's just a definition of a wave. There is the wavelength, there is the distance from the middle all the way up here. We call this amplitude. This is amplitude. All right, amplitude. So here is the wavelength, and the number of waves passing a given point per second is called frequency. Frequency, like that, is simply a number of complete, you say complete, what complete waves passing given point per second. It's just the definition of frequency. We use this symbol right here, the sacred symbol for nu. You just say nu. It doesn't look like a V, but italic V. This is the symbol for frequency. Symbol for frequency. And for us to understand the electronic structure of atom, there is a need to understand the electromagnetic radiation. Electromagnetic radiation is just part of electromagnetic spectrum, which we will look at later. All right. Electromagnetic radiation, just like wave, have some speed. All right. So this is right here, the wavelength, the frequency, and then the amplitude. Amplitude, you gotta know what an amplitude is. It's the distance to the height of the wave is called the amplitude. This is the amplitude, and this represent what? Represent the intensity of light. It represents, that's the distance from the middle of the wave to the peak. From the middle of the wave to the peak of the wave is the amplitude. Now, all electromagnetic radiation move through space with a constant speed we call speed of light. This c is the speed of electromagnetic wave or radiation, c. And the constant value for this is 3.0 times 10 raised to positive 8 meters per second. Please remember the units. This is the speed of what? Speed of light. We call this simply speed of what? Speed of light. Some of you may have covered in physics, or you may have seen this value, or simply the speed of light in a vacuum. Okay, in a space we use c. Now the distance between two, I've just explained this, between two corresponding or adjacent peaks is the wavelength. Then we use the lambda sign. This is something you need to know, because we'll come up with an equation. Frequency, this is not phi, but it is Greek symbol for nu, and it stands for the number of waves passing at given point per unit time. Now this V is simply units. Units is given in per second, or when you look at this, it's the same thing, or hertz is the same thing. Hertz, they all represent this unit for frequencies. You can change to using the abbreviation we learned earlier on, megahertz, gigahertz. All those are just different units you can, or you will come across, you may come across in expressing the frequency. So know that, so that when you look at this, per second, it's the same as hertz. It's the same as hertz. Please take note of these. Hertz is the same as per second, or 1/2. This is the same thing. This is the same thing as that. Now, if you look at the two waves here, two waves in A, this has a longer wavelength, this has a shorter wavelength. The frequency here is high, the frequency here is low, okay? And this is the amplitude. Typical question you will see in exam is the vertical height of a wave is called what? The vertical. So assuming that you are making your own notes, this is the vertical height. We call this vertical height, so that you don't make mistake. Of course, it's not wavelength. Amplitude, that is the correct. This is the correct answer for this question. Okay. So I'll say this is B. amplitude. Amplitude. Frequency is just the number of waves. We don't have anything to do with D or E. Okay, E or D is non-existent. So electromagnetic radiation comprises all the waves, or it's just the radiant energy. Even though you will see once in a while gamma, X-ray, ultraviolet, microwave, and radio waves, of importance is the visible region of electromagnetic radiation. What do we mean by visible? You see visible part of electromagnetic radiation, okay? Visible part is this region we can see with our naked eye, and if the wavelength, which you know now, the wavelength ranges from 400 to 700, it falls under the visible region of electromagnetic radiation or radiant energy we can see with our naked eye. If you look at this color coding, it represents the trend in the wavelength, For example, without, okay, I want you to learn, commit your memory, is this wavelength, so that you say Richard of York grow bananas in vain. That's how the colors on the visible region are arranged according to increasing the wavelength. On this side, this is a high frequency, high energy, more energetic, all right? And here, shorter wavelength. Here is longer wavelength, all right? On this region, longer wavelength, low energy, and low energy, high frequency, low frequency as well. You need to know, so that I can, you can make a conclusion that yellow line, you better know what this means. This is violet. This is indigo. This is blue. This is green. This is what? Yellow. This is orange. Orange. Shall I have this orange? Shall I have this orange? And this is, of course, a red. You should know those red. Question from here is, arrange the following according to increase in energy or increase in wavelength, or which one of the two colors has high energy or low energy. Based on this, memorize, commit to your memory, and this falls under the what? The visible region of electromagnetic radiation. Here we have 400 or 400 nanometers, and this is 750 nanometers. Understand what this means. This is the wavelength. All right, we're talking about the wavelength. We're talking about the wavelength, so that you know, all right, you know how to relate the energy with this region. What you see here, this is the wavelength in meters. Now, gave you this value earlier on. This is the speed of light. Speed of light, you will be given that value. I'll give you in the exam, all right? It's a constant which you need to use. There is an equation here which I want you to understand and know how to use in. Now, wavelength is the same as speed of light of the frequency. You see that? And remember, the units here is in meters, or I should have just have this as units, all right? Units, this is meters per watt, meters per second. This is frequency, should be frequency in hertz or per second. All right. If it is in megahertz, if it is in other units, you need to change the frequency to hertz or per second. Frequency to hertz or per second. Now, this main equation we can rearrange. Of course, no one will ask you to determine or calculate the speed of light. It's given that, but frequency on the other side is given by c, which is constant of the wavelength, and this is in meters per second. So this one should be what? Should be in meters. So if it is in something else, such as nanometers or angstrom, you need to change to meters. And remember, the unit C, all right, C is always 3.00 times 10 raised to 8 meters per second. Meters per second. All right, meters per second, you'll be given that. So you should be able to rearrange this equation, because question will come either in the quiz or in the next exam. Let's see an example here in practice exercise 2, practice exercise 2, all right? Here, practice. We can do exercise 1. This is a worked example in the text. All right, exercise 2. How will you answer this question? Look at this. This is what I'm looking for. All right. If you look at the question, this is the question. Which type of visible light has a longer wavelength? Here is red, here is blue. All right, some of you may think that you need to be given numerical values. How do I know? Is there somewhere where we are given the numerical values for the wavelength of different colors? Nope. All you have to remember is the general concept. This is what I gave you here, all right? If you look at the position of red with respect to blue, if I remember this, and I know you may have memorized in high school, and there is mnemonic way of committing to your memory. Richard of York crossed bananas in vain, all right? So red and blue means, look at this, longer wavelength. I see blue, blue is right here and red is here. So the one with the longer wavelength will be red. So this is red, all right, red. All right, red. Let's see A. How will you do again? I know we covered that. Let's see one. A source of radiation produces infrared light. Which one of the following will be the wavelength of light? If you look at this, that means you need to also learn this infrared here. Just after the visible region, infrared, the wavelength is in the range of 10 to -5. And remember, micro, all right, micro equals to, or rather, let me just say micrometer equals to 1 times 10 raised to -6 meters. If we go by the given units, 3 nanometers, no, that's way too big. Micro, it cannot be a centimeters. This is too big. This is too big. This is too big. And by the way, this is angstrom. 1 angstrom equals to 1 times 10 raised to negative what? Negative 10 meters. 1 angstrom, which is too big. The only one which is closer to micrometers is D. So that is D, which is 34.5 micrometers. Could be, you see this could be, because it is in micrometers range. So if you look at this from here, the micro range is in this. All right, micro. It cannot be the other given. All right, here is another question. If wave A, which is season, this is a learning check. If wave A has a wavelength of 2.0 meters and a frequency of 1.5 times 10 to +8 cycles per second. This is the same as 1.5, by the way, times 10 to 8 hertz. All right, times 10 to 8 hertz, or 1.5 times 10 to 8 per second. It's the same thing, cycle per second. What are the wavelength and frequency of B? There is no calculation here, but it's just a question of eyeballing and comparing the wavelength in order to make a conclusion which one is the most or could be. If I look at the wavelength, for example, it looks like the wavelength of wave B is half the wavelength of wave A. The wavelength of wave B is half the wavelength of B. It's almost half. So if I know the wavelength to be 2 meters, and then makes sense that the wavelength of B is 1 meter. And using elimination method, all right, using elimination method, it cannot have the same wavelength. Look at this. How can this be the same as that? It cannot be B. It cannot be shorter than all the way, like, 4 times shorter. But these C and D are wrong, and the most appropriate answer is A. The correct answer is A for that, based on just looking at the wavelength and because even if you look at the frequencies, look like it's twice, twice the frequency is higher than, it's almost twice, so it's going to be 3.0, 2 times the frequency for wave A. All right, to use this the equation we looked earlier on, let's see, calculate the frequency of green light emitted by a hydrogen atom with a wavelength of 486.1 nanometers. Now, well, in this example, all right, in this example, you need to recall what we learned earlier on about the Greek prefixes. when we say nanometer, when we say megameter, when we say terameter. What does that mean? What have you multiplied the base unit of length by what numerical value? Before we look at that, we are calculating the frequency. Given this equation, I'm gonna give you this in the exam, all right, where Z equals to 3.0 times 10 raised to 8 meters per second. We are calculating frequency. It's given by C over lambda. You have to know the symbols. This one, this is frequency. This is the frequency. Now, since the units are in meters per second, we need to change the wavelength to meters. You can't just plug in the numerical value given. You may see the multiple choice, but that does not mean correct. So at the back, you need to recall, and this is something you will not be given. 1 meter equals to 1 times 10 raised to 9 nanometers, or 1 nanometer equals to 1 times 10 raised to what? Times 10 raised to negative 9 meters. Whichever way you choose, this is something you need to remember. And I picked this because of the units. Now, let's change wavelength is given by, or in meters, 486.1 nanometers times, I want to get rid of nanometer. I want to remain with meter. Why am I doing this? Because of the speed of light, which is in meters per second. So here, 1 meter is the same as 1 nanometer is the same as 1 times 10 raised to negative 9. This is negative 9 meters, and this is a nanometer. So this and this will cancel, and we have 4.861 times 10 raised to negative 7 meters. Now we can now use this to plug it in the equation, in this equation right here. This is what we will plug it down here. So that, all right, we say therefore frequency equals to 3 over wavelength, 3.00 times 10 raised to what, 8 meters per second over 4.861 times 10 raised to negative 7. This is meters, and then meters and meters will go. And if you look at the units cancellation, these will go and that will go. All right, and whatever will remain, it will be per second, and this will be 6.17 times 10 raised to 14 hertz per second. That is how you write with the correct number of units. Because of the 3 significant figures here, we use 3 significant figures. In our final answer, please don't forget the units. Don't forget the units. So this is an opportunity to go back and learn the prefixes we looked earlier on, because next time this might be in kilometers, this might be in centimeters, this might be in micrometers, this might be in gigameters and so forth. You need to change to meters. You need to change to meters using appropriate conversion factor, So here are some of the units associated with electromagnetic radiation, and note the numerical value so that you generate the conversion factor. All right. For example, here, 1 angstrom, and this is something you may have seen in physics, equals to 1 times 10 raised to negative 10 meters. That's what that means. 1 nanometer, this is what I use, 1 times 10 raised to negative 9 meters. So what you see here, you know, it represents 1. For example, I know you know this, 1 kilometer equals to 1,000 meters. Meter, this is the base unit in what? Base unit in metric for the distance, or no, not distance, but for length. This is for length, all right? Length, all right, for length. All right, so those are, this is just an example, but the most important thing is right here, micrometer and so forth. Those are the units. You'll see that many types of electromagnetic radiation. I want you to just go practice more on how to use that equation. Okay, use that equation. Now we have looked at the properties of light, and it does not explain, or at this point, the properties of light being wave-like in nature in relation to electronic structure does not explain what scientists in 17th century observed at that time. All right. We cannot at this point, you know, relate the observation scientists made in 17th century, and there are 2 types of observation, or 3 types of observation. One is the black body radiation. The wave nature of light does not explain that. The photoelectric effect, which we are going to explain that, the wave nature does not explain that. All right, and then the emission spectrum. Spectra for many, spectrum for one, the wave nature does not explain. So here, electronic properties not explained by waves, by the wave nature. These were the observed properties at that time, and they were associated with how atoms interact with electromagnetic radiation. Now, what is black body radiation? Black body radiation is simply the emission of light by heated object, all right, which were plugged before that. Take, for example, the cooking stove, right? When it's off, it's plugged, it doesn't emit any light. But if you turn it on, crank it up all the way in a dark room and cut it off, it will still be giving away light. We call that black body radiation. Here is an example on some demonstration where a nail, a piece of nail, is subjected to high temperature. And if you take off this will continue glowing, it will continue emitting light. We call this black body radiation. Now, German scientist by the name Max Planck explained the black body radiation using what we call quanta. From the word quantum, quanta is many, singular is quantum. He proposed that light is emitted in discrete values, which we call quanta, like assuming that it's only one. Remember, when we say explaining, he's explaining the black body radiation here. Like, why do objects subjected to high temperature emit light afterwards? And he's saying that energy comes in small packets called quantas. According to Max Planck, quantum is a packet of light, right? Like a small particle, but of course many, and as opposed to just continuous. So he's saying that the light coming from the hot object, they are emitted inward in small packet. That's what he just proposed, that light emitted by hot object come in small packets, which we call quanta for one, quanta for many. Now, there is another observation which was made in 17th century. We call it photoelectric effect. This was according to Max Planck. All right. Sometimes you need to make your own notes about these personalities. You may be given also a question down the line, and if you don't know who did what, it will be a challenging. So here, Planck is proposing that photo object are, or rather light is emitted by hot object in small packets we call quanta. For photoelectric effect, let's see first of all, what is photoelectric effect? Photoelectric effect is that when light is shown on a metallic surface, they eject, or electrons are ejected. Albert Einstein explained the photoelectric effect. Photoelectric effect simply states that what? When light is shown on a metallic surface, electrons are emitted, and each electron or each metal has a different energy at which electrons are ejected. So in other words, if light is in small packets, remember now, even I should have that electrons is coming like a wave now in small packet. And this is a metal surface. If it hits on the metal surface, electrons are ejected. These are electrons being ejected from the surface. This was for the electric effect. Albert Einstein concluded that energy is proportional to the frequency. The minimum energy required to eject the electron from the metal surface is proportional to the frequency, which is actually in line to what Max Planck proposed, that energy, or rather the energy from the hot object, are quantized. So here is the energy, E, this is energy, is proportional to HV. And you need to know that this is what we call Planck's constant. You don't need to remember, but I'll give you this. It has this numerical value, 626 times 10 raised to negative 34 joules per second, times negative 34 joules per second. This is frequency. Here, this is or per second. So here we can calculate the energy. We can calculate the energy of one, all right, photon. We can calculate the energy of one photon. This is energy we can calculate the energy of a photon. A photon is simply here. Let's see this so that before we do that, photon, this is simply a photon is a packet of light. So here, energy of one photon, calculate the energy of one photon of yellow light that has a wavelength. Remember again what I said earlier on. So if we're calculating E of photon here, this is given by Planck's constant times the frequency, where sometimes you may not be given frequency is given by the speed of light over the wavelength, which means therefore E over photon equals to C over the wavelength of the wavelength, because this is frequency. And remember, C is the speed of light, 3.00 times 10 raised to 8 meters per second. So it may not be obvious, and this has to be in, this is wavelength in meters. You need to change that to meters. This is a worked example which I want just real quick show you how to find the energy. So if we know this is the equation which I'll give you in my formula sheet, remember the subscript here, photon. This is the energy of one photon. If you plug in, it's going to be frequency is C over the wavelength. What is happening here is just rearranging that. On the whiteboard, frequency is the speed of light over the wavelength. Please take note of how the wavelength in nanometers has been changed to meters because of what? The speed of light has units of meters per second. How we change that? All right. It is 589 nanometers times, if you want to know 1 nanometer, and then 1 times 10 to -9 meters. Nanometers and nanometers will go. And this is 5.89. It's the same thing, times 10 raised to -7 meters. This is the value you just have, like, and we have the frequency, so that we now multiply the Planck's constant, which is the H here, to be given that unit reconciliation, and this is in joules. This is in joules. But it was given here 3 significant figures, 3 significant. We express our final answer with the 3 significant figures. So remember, this equation here is energy for 1 photon of light. It is energy for one. This is for 1 photon of light. All right. You'll be given that down the line. So remember to do that. You can be asked for 1 mole if 1 photon of radiant energy calculate the energy for 1 mole of these photons. So you divide the photons per mole by the energy to get for 1. So if this is for 1 photon, this is the energy for 1 photon. Remember 1 mole of photon equals to 6.02 times 10 raised to 23 photons. Why are we bringing, or why am I bringing up this? Because from here, if this is the energy of 1 photon, you may be asked for what will be the energy for 1 mole of photon. 1 mole of photon, that means you multiply by the Avogadro number here, this value by the Avogadro number to get the what? To get the energy of 1 mole. We calculate that 1 mole of these photons will supply. Again, this is something you need to remember. No one will tell you what the definition of a mole. No one will tell you. This is something you need to remember. You may have learned at the beginning or even in intro that 1 mole of anything contains Avogadro's number of things. That's why I'm picking up this number. And in case you're wondering where this came from, it's because of the definition of 1 mole. Definition of 1 mole. Let's see. Here is another example. Learning check. Let's see. Calculate the energy of orange light emitted per photon of neon sign with the frequency. All right. So we know the frequency. We know the frequency. So here, energy. All right, energy over photon equals to the Planck's constant times the frequency, where H is 60 times 10 raised to negative 34 joules per second. And you are given already, this is per second, hertz per second. This is 4.89 times 10 raised to what? Times 10 raised to 14. And this is per second, like that. Hertz is per second. Therefore, all right, therefore, E photon for 1 photon equals to 6.626 10 to negative 34 joules times seconds times 4.89 times 10 to 14 per second. So that per second will go with per second, and we will remain with joules. We will remain with joules. All right. In joules. If we want to change to kilojoules, that's fine. But nevertheless, here is the answer: 3.24 times 10 raised to negative 19 joules. SI units, joules. So remember that, double check. That is how to find the energy. Again, I want to emphasize that if the frequency is in megahertz, mega, you have multiplied by what? Go back again. If it is in gigahertz, if it is in kilohertz, you need to convert to hertz, and hertz is the same as per second. Hertz is the same as per second. So if we were looking for 1 mole of this yellow or orange light, we multiply by Avogadro number. That's all what we had to do for that. That's what we had to do for that. Now, that take care of section 6.2. 6.2. Still, we haven't tagged the properties of light to atomic structure. All right. We are just trying to explain the observation, right? The quanta, the photon, how to calculate the energy of one photon in an attempt to explain the photoelectric effect that light is given up in small packets we call photon, and we can calculate the energy of one photon. We have seen it here. Now, atomic spectrum, atomic emission, all right, rather emission to emit something. What you see on the PowerPoint slide here is two gas discharge tubes. A class discharge tube in with gases, different gases in low pressure. If we have, let's say, for example, neon, this is a discharge tube for neon gas. The neon gas is in this. If we have, if we apply electric current on both terminals for this gas, they emit light of characteristic wavelength. Hydrogen, see this color, neon, we need this color. We call these discharge tubes. And from the word emission, we'll see later on. One of the mystery which could not be explained is the emission spectrum. And what that means is there was some lines, you know. I'm just gonna draw this. Representing lines. And the emission spectrum is just a spectrum. This is a spectrum right here. For one, showing different what? You see different lines? In 20th century, scientists could not explain why they could see different lines, all right, for different discharge tubes. Here is for neon, here is for what? For hydrogen. It's the same one we have here. This is the discharge tube using Handel spectroscopy. You may see the lines right here. It was a mystery that what is it really causing these lines? This is emission spectra for hydrogen discharge lamp. This is for neon. There is a continuous, spectrum, which is, you see the red is merging on to yellow is going to create, it's a continuous fastest line spectrum. Let's keep an eye on line spectrum. And again, remember the visible region. Remember the visible region of electromagnetic. Other than that, we wouldn't be able to see those radiation. You can't see X-ray, you can see microwave, but if the wavelength here, see violet, you see red, yellow somewhere. Only line spectrum for discrete wavelength, discrete, that we can describe that were unique, and they could not explain what is causing in here. It is a mystery that they could see different ones, different lines, and efforts were made to explain this observation for different. And remember, where we are going with this is using the electronic structure. Somebody will explain that using electronic structure of an atom. So bear in mind that an effort is being made here to do it, to explain why we see different lines, especially for hydrogen. We know hydrogen has one electron, it's one electron system. But why is it that we have 4 lines? 1, 2, 3, 4. Shouldn't it not have been one line for one electron system. We'll see later on why we see 4 lines. It's a mystery. Stay with me. Somebody else, he was an English teacher, I believe. Yeah, John Palmer came up with a formula here, simple formula to calculate what? To calculate the wavelength for violet, for indigo, for blue, for red. He came up with a formula which we call Rayleigh-Spark equation. He came up with that. Rayleigh-Spark, John Palmer. We can calculate the wavelength. This has nothing to do with the other equation, and you will be given these 2 equations, know when to use which equation. This is the reciprocal 1 over the wavelength. So on the left side of the equation, 1 over the wavelength is given by RH. We call this rate, no, right, Y, right back, what? Constant. Again, I'll give you that value is 1.097 times 10 raised to 7 per meter. Please remember the units. It's per meter. Now, 1 over 1 or n square minus 1 over n 2 square. Let's deconstruct this equation and understand where these letters stand for. This constant. This is just a constant which, when plugging this formula, we call Rayleigh-Spark equation. He explained that the reason we see these lines, or how to calculate this, it has to do with electrons dropping from a high energy level to a low energy level. And where we are coming with this is this, that if we subject the gas atoms in each of these discharge with some energy from electricity, of course, they get excited, or rather excited. Let's say this, let's go back to Bohr's model of an atom and have electron here. And if light is coming right here, it interacts with this electron, and this electron we say that this is excited, what? Excite electron. It is promoted to a higher energy level because this is energy, all right? Interact with the electron, it gets excited, it goes up, and then when it did drop like that, depending on where it's dropping, light, or rather here, this is a photon given up, and depending on the wavelength of that photon, you will see it as a different, all right, electron is coming back to where it was, a photon is given off, and depending on the which energy level is dropping from, we see these lines with these, see these lines. Now, we can calculate the wavelength. Maybe this is around 390. All right. Maybe this is 5 something, and this is around 6. We can plug in that. This is in this equation right here. So if the equation is dropping from energy level 1, this is stand for energy level, energy level 1, energy level 2. You see this? N equals to 1, N equals to 2, N equals to 3, N equals to 4, and so forth. So that this N stand for the energy level. This stand for energy level, and you square those so that eventually you will do what? You will flip the equation so that to get the wavelength of this line. Now, Bohr explained why we see this line. It has to do with the electron dropping. Remember, this is Bohr's model of an atom, that electron move around the nucleus following. Maybe you can go back to here. Let's see. Electrons moving around the nucleus. You see the electrons moving around the nucleus. Let's see hydrogen. This is hydrogen, all right? This is hydrogen. You see one electron is moving around the nucleus. You see electron is moving down the nucleus. All right, that's one electron. If it is two electron system, that is helium, you see the electrons are moving. Suppose we have many electrons, how will they move? Let's say magnesium. You see how the electrons are moving around the nucleus? Yes. And now, all right, now with that, these are energy level. You square those, and we can calculate the wavelength. Remember, transitioning here, this is what I explained on my whiteboard, that dropping from. So if you look at the transition, when an electron in hydrogen atom move from n equals to 6 to n equals to 1, dash of light of dash nanometers is emitted. So how are you going to do that? Are you going to do that? When I see that I have two energy level, that means we need to calculate the wavelength in nanometers. And remember, because of Rayleigh constant, we'll have to work in meters first and then we change to nanometers. So let's see. With this, we know from the Rayleigh equation, 1 over lambda equals to RH into 1 over n1 square minus 1 over n2 square. This will be 1.09. I'm going to give you this 0.97. This will be given in the exam. 7 times 10 raised to 7, 1 over m over 1 over 1 square minus 1 over 6 square. All right. 1 over 6 square. So this will be if you plug in that will be 1, or on this side 1 over lambda equals to 1 106 All right, 527.78. All right, over 1. If we flip that, that means lambda equals to 9.38, sorry, that 9.308 meters. But the question here is, we want to find in nanometers. So I'm just going to change that to nanometers using this conversion factor, that 1 meter equals to 1 times 10 raised to 9 nanometers. So that if I cancel that, and that will cancel, and this will be 9.38 times 10 raised to 1. All right, nanometers. Nanometers is just going to be, you multiply that, it's going to give you the value in nanometers. Still, 1 nanometer, you can use any times 10, 1 times 10 negative 9 meters, or 1 meter equals to 1 times 10 raised to 9 nanometers. Whichever way, you need to remember this. You may have to write the equation again, but please remember to set up your problem, look at the setup, unit cancellation, and know how to use your calculator. All right, I know in Honalog, please learn how to use the Honalog to handle exponential or numbers in scientific notation. Let's see the Potts model of an atom, now explaining that the reason why we see different light has to do with the transitioning of electron from excited state to ground state. We call this ground state, right? Where it was originally, we call it ground state. All right, versus the excited state right there. Versus the excited state right there. So no Potts model of an atom. Okay, when we say model, it's model of an atom, and what you see here, that electrons move around the nucleus following specific radius. A radius you see here, we saw it earlier on. All right, the radius from multi-electron. Look at that. You see this? This is rubidium. Electron move around the nucleus following specific what? Specific radius from the nucleus with a specific, so that when it's transition, it's gonna do or emit electrons. So here is the ground state, negative 218. If you look at the energy within an atom, this is shell number 1, this is shell number 2, number 3, number 4, all the way to infinity. And if you look at the ground state, this means where the electron was. If you look at our ground state here, closer to the nucleus. If an electron is transitioning from ground state to a higher energy level, energy is observed and it is positive. That means N1 or initially is 1 and final is greater than 1. It can be either 3, but always the energy is positive. For energy being given off, it's transitioning from higher energy to lower energy. That means final is less than 1 energy, or change in energy is less than 0. Look at this constant, because we are going to use that negative 218. We are going to use that to find the energy of an electron. So remember, electron or an electron is only permitted to move around the nucleus in certain allowed energy level or energy state, energy level 1, energy level 2. It cannot be just in between two energy levels. An electron in an allowed energy state does not radiate energy. An atom, therefore, does not spiral into the nucleus. So he's explaining that why is it not that if electrons are negatively charged and protons are positively charged, why is it not that this electron is crashing into the nucleus? It's because of what? They move around the nucleus in only certain specific region, and we can calculate the energy of each level. Energy is emitted. Of course, I explained that energy is emitted or absorbed. Please, emitted or absorbed. When? Look at the transition. If it is moving from lower to higher, energy is absorbed. If it is transitioning from higher to low, energy is given up, and we can calculate the energy emitted or absorbed using that. That's what we looked earlier on. Okay. Well, electron in the lowest energy level, we call it ground state. Please remember that ground state I used earlier on, excited for that, all right? To move electron in a higher energy level, excited, moving that. The change in energy, look at this change in energy, negative 2.18, when we had it with a constant seal times 10 to negative 18 joules. This is the final, this is the initial, where the electron are transitioning from energy level 1 or energy level 2. This is a constant, just like the Rayleigh equation, that you need to remember is always negative, so that change in energy between the energy level, change in energy, change between two orbits is given by negative 2.18 times 10 to negative 18, which is constant. Plug it in this equation to get the energy level between two orbits. And what I have underlined there is orbit right here. This is just a region of space in an atom probability of finding an electron, right? This regional space where you can find an electron, we call regional space. It's just this is just orbital. I wanted to say this is orbital. We'll come back to this. I know you have looked at this, but orbit, which is now simply circular path around an object. That's how you define what? You define the orbit. I had to highlight this so that you know the difference between orbit and orbital. Hold on to this, we'll come back to that. You're gonna draw a parallel between the two. Let's see how the energy is calculated. Transitioning of what? Electron from higher, and the effort here is to explain the lines that when electrons drop down, depending on the wavelength of the light, the photons being given off, you'll see it as red, you'll see it as yellow, you'll see it as blue. Now, we can calculate the energy, all right, based on or given, remember, energy or change, all right, energy is given by negative 2.18 times 10 raised to negative 18 joules into 1. So this one is what? Transitioning from 1. So 2. Final is 3 square minus 1 of this is the initial where it's starting from, 1 square. That's what, or how you set up the what? That's how you set up the equation. That's how you set up the equation. It turns out that this is 1.94 times 10 raised to negative 18 joules. This is the energy. And if you think it is positive because it is transitioning to go from lower to upper, energy as is observed. Energy is observed. Please take note of the sign, because sometimes the multiple choice could be negative, the signs could be positive. Suppose we had negative 1.94 times 10 to negative 18. How will you make, or how will you know that this is the right one? How will you differentiate that? N equals to 1 to n equals to 3, that means it is positive. You see here, going up from lower to here, change in energy is always positive, but it's coming down, all right, energy is given out. Paul explain what, or the lines, what is happening, but there are some limitation for this. There's some limitation. It only works for hydrogen. It didn't work for multi-electron systems such as what? Such as helium, such as lithium. Any system with more than one electron, it didn't work. Yeah, so that will not work because of the classical physics. You know, positive, negative to attract. Here, electron could just fall into the positively charged nucleus because of the protons in the nucleus. Well, circular motion is not wave like nature. We know that, or we looked earlier on, that light behave as a wave, but Bohr is explaining and saying that electrons move around the nucleus in a circle without explaining the wave. So in other words, if this is the nucleus, we expect the electrons to be moving around the nucleus like a wave. But with him, he says circular like that, circular like that. He didn't explain the wave nature. Circular motion is not like, but we know light behaves a wave. But it's important though. This was the foundation for what we will see later on, that electrons, all right, for sure, we know electrons occupy specific energy levels. What we know from Bohr's model is that electron exists in certain discrete energy level. We will look later on, we call those quantum numbers. We're going to come back to quantum numbers later on, the energy levels, which is true. Energy is involved in transition from an electron from one level. So here, for an electron to move from ground state, if this is the ground state right here, and this is the excited state right here, energy must be involved, which is true. So the first two statements there, as far as the Bohr's model is concerned, is true. This is true. We'll see quantum numbers later on, but remember, for electron transitioning from one energy level to another energy level, energy is involved. We have calculated the energy. Now, somebody else by the name, all right, which we are going to look at it right now, is the wave nature of matter. What does this have to do? Section 6.4, we know light behave as matter. I'll label this as dual nature of light. One, behave, what we already know, behave as a wave. Wavelength, all right, frequency. Look at that, this is wave. And then two here, as matter. We talk about photon, all right? Remember photon? A particle of light. This is particle of light here. Just gonna make this particle of light like that, particle of light, which means light behave as a matter, even though it doesn't occupy space, right? It cannot volume. You cannot say this is the volume of light, but it is behaving like matter. Now, somebody else came and say, and that's the subject of section 6.4, that if light behave as, we call de Broglie right here, all right? De Broglie right here, we see somebody by the name de Broglie. Proposed that if light behave like matter, and then matter also matter. In other words, if light has a wavelength, that means even matter also has, or if matter has a wavelength, light has a behave like matter. Matter can also have or behave like light. That means matter has a wavelength, and we will always be talking about the de Broglie wavelength. Okay, the wavelength of matter, Louis de Broglie. And that's a French scientist who proposed that matter behave like light. We call this the wave de Broglie. Please don't confuse and don't confuse. Let me draw this parallel right here and just be specific. And you'll see wavelength. You will see these two equations. Lambda equals to C over frequency. And then this is called the de Broglie wavelength over V, where H, Planck's constant, this is mass in kg, and then V is not frequency, but this is velocity. This is speed in meters per second, You need to be changing those sort of, when you're given a problem, and that's what is the de Broglie wavelength of something. This is what we need to remember. Mass should be in kilogram, all right? Remember the mass should be in kg. Speed should be in meters per second. You may be given in miles per hour, kilometers per hour, all right? You will need to change to what? Change the speed to meters per second and mass to be in kilogram for that. For example, here, let's see worked example on exercise 6.5 on de Broglie equation. What is the wavelength of an electromagnetic, no, of an electron moving with a speed? Maybe I should blow this up, all right? So that we look at that, what is the wavelength of an electron moving with a speed of? So we know the speed, as the velocity in meters per second. We don't need to change that. The mass of an electron, you will be given this, you don't need to remember that. So we know electron is matter, so we will need the de Broglie. It's not light, so you have to know that this is a de Broglie. Some question will be de Broglie wavelength. Just plug it in the equation. You will be given this value. You don't have to worry about the numerical value for H, which is Planck constant. You'll be given that this is what you need to know. Commit to your memory how you maneuver or crunch the numbers until you get the wavelength. Okay, this is Planck constant. Look at the the mass of electron is in kilogram. Remember what I said earlier on, mass should be in kilogram. If you look at the speed, I don't need to change. It's already given in meters per second. You gotta be careful because sometimes you may be given in miles per hour or kilometers per hour, change to meters per second. All right. And the reason why you see this is we need to change or reconcile the units so that we remain with meters. Kilogram, kilogram. This is just for unit cancellation. Kilogram and kilogram to go away, and then joules and joules in Planck's constant. And then our second here will go with the second here. Will remain with 1 second, and then the second will go with another second here, and then the all of this is gone because of the meter here will go with the 1 meter will remain with 1 meter, and all will be in 1 meter. So if we change that to 8 meters or angstrom, whichever way you're looking, okay, whichever way you're looking. In case you want to know where this comes from, we just minimize that. All right. I'm going to minimize this and show you that if it is 1 point, all right, 1.22 times 10 raised to negative 10 meters, right, equals, or if I want to change to nanometers, look at this. I want to get rid of meters. I want to remain with nanometers. This will be 1 meter. This will be times 10 raised to 9 nanometers. That and that will go. And this will be 1.22 times 10 raised to negative 1 nanometer. So if you change that across, all right, if you change that across or take that across, this will be 0.122 times 10 raised, no, times, but it's just gonna be nanometers. This is nanometers. If you want to change to angstrom, all right, it's 1.22 times 10 raised to negative 10 meters. 1 times 10 raised to negative 10 meters equals to 1 angstrom, like that. So if you take that across to equal signs 1.22 times 10 raised, not times 10 raised, but angstrom, it's 10 and 10 will cancel. You remain with that. These are some of the concept on dimensional analysis. Please solve more problems on this de Broglie wave equation. The most students not really like, they don't know how to identify which equation, which formula they need to use in an exam or a quiz, but forgetting to recall some of the concept we learned earlier on, like for example, changing from angstrom to nanometers, from nanometers to centimeters to move forward. So please remember that. Here is another example on de Broglie equation. What is the de Broglie wavelength? This is specific. So here we are looking for the de Broglie wavelength. I'm gonna plug in that. All right. This will be mass in kilogram times velocity in or speed in meters per second. So here this is the speed in meters per second, which is equals to 5.0 meters per second. Mass is 0.025 kg. I had to convert that. So that this will be 6.6, all right, 6.626 times 10 raised to negative 34. This is Planck's constant over mass, which is 0.025 kg times speed, which is 5.0 meters per second, then times 1 joule equals to, this is something we looked at in chapter 1, I believe, kinetic energy. So that joules and weight will go with 1, that will go with that, that will go with that, we'll remain with meters. Gonna go with that, and this is 5.30 times 10 raised to negative 3 joules, negative 33 joules. This is 33 right here. Please double check. This is how you calculate de Broglie wave. And remember what is all about that. De Broglie is suggesting that if light is behaving like matter, then we can calculate the wavelength of any object. You may see in the exam, calculate the wavelength of a baseball, calculate the wavelength of a plane or anything, any object, but you'll be given other parameters, of course. But remember to change the mass always to kilogram. Change the speed always to meters per second before you reconcile. And this last conversion factor here is so that you remain with the correct units. By the way, this is wavelength. I meant to say the wavelength here is meters, not joules. Meters, not joules. Looking for the wavelength. Looking for the wavelength in meters. And that is two significant figures. It's gonna be 3. It's gonna be 3 right here. 3, which is B. This is B. All right. Is from setting that. Now back to our model of an atom. We're still on the model of an atom, and what we are suggesting or what we know now is electrons are moving around the nucleus now like a wave, is behaving like a wave. It's behaving like a wave, like that. These are electrons moving around the nucleus like a wave, because we know from de Broglie that matter can behave like a wave. So electron is moving around the nucleus like a wave. Uncertainty principle, Heisenberg uncertainty principle is another scientist who proposed that there is no way we can know the location of the electron and at the same time know its speed. It's just like having a supersonic jet. Before you know it, it's gone. Like if it's moving at a high speed, there's no way we can know for sure it is at this location, because the more we know it's at this, it must be standing right there. And the more we are certain about this, the location, the speed is, is compromised. Maybe if I bring this analogy here of uncertainty, let's say here, how do we know the location of those electrons? You see this? Or even maybe one system like that. We don't know the location. The more we know, all right, the more we know the location is gone, the more we know it's gone, it's going. So there's no way we can know the exact location of this one electron in hydrogen, and at the same time know the position, and at the same time know the position. This is the Heisenberg uncertainty principle, that there is no way we can know the exact location and the momentum. This is X. Uncertain, you are not certain. Position, you have to know X is position. And this is uncertainty in velocity, uncertainty in velocity. And by the way, this is change uncertainty in momentum, mass times all right, mass times speed is momentum. Mass times speed in momentum. And just like before, m is mass in what? Mass in kilogram. And this is velocity in meters per second, So there are two things you can be asked in Heisenberg uncertainty principles, that uncertainty in position, uncertainty in momentum, or uncertainty in velocity or speed. So the H is Planck constant. This is 6.626 times 10 raised to negative 34 joules time a second. This is Planck's constant. And of course, this is pi, which is 3.14, right? 3.14. So if we are asked uncertainty, all right, and uncertainty in position, like that, uncertainty in position will be change uncertainty in position equals to Planck's constant over 4 times pi times uncertainty in, or mass times uncertainty in velocity. This is uncertainty in velocity, so it's going to be what this is uncertainty in what? Uncertainty in velocity, like that. And then, and in velocity, in momentum. Over 4 pi times uncertainty in position, x, like that. All right, uncertainty in momentum. And then uncertainty uncertainty in position. And remember to change the units. You have to change the units. So this is equation 3. This is equation 2, and this is equation 1. So you have to know which one you are going to use. In the exam, you're just gonna get this one. You're gonna get this one. And where we are going with this equation is the position of electron in an atom. And Heisenberg came up with the principle that it's hard to know the position of an electron at the same time the speed. And this is all about the Heisenberg uncertainty in position. Here is an example on how you can be tested on Heisenberg uncertainty principle. Using the principle, calculate the uncertainty in position of 1.50 milligram of a mosquito moving at 1.40 meters per second if the speed is unknown, all right, plus or minus 0.1 meter per second. This is problem number 6.51, all right, on page 251. What you see here, this is and plus or minus velocity or speed. Already we are given in meters per second, so we don't need to do that. Mass (50 milligram) times, you got to know that 1 milligram or 1,000 milligram is 1 gram times 1,000 gram equals to 1 kg. We need to change the mass to kilogram, and this will be 1.50 times 10 raised to -4 kg. Mass has to be in kg. Well, the rest, once we know the mass, therefore, uncertainty in what? Position. This is given by the Planck's constant over 4 pi times mass times change in velocity. This is 6.626 times 10 raised to -34 joules times second, all right, over 4 times 3.14 times 1.50 times 10 to negative 4 kg times 0.01 meters per second, and we need to reconcile the units. Remember, time is 1 joule kg times meter square over square, so that this and this will go. All right, this and this will go. This and this will go. Let me see if I have another one. Maybe yellow. Second and second go. And then finally meter and meter will go, and then we remain with meter. So if we reconcile these units, we will remain with meter, which is the unit for position in meters, uncertainty in meters. This will be 4.3 because of one significant figure. You'll see on the calculator is 3.5. All right, you'll see this will be 3.5. 3.5 times 10 raised to negative 29 meters, but because of one significant figure, 4 times 10 raised to negative 29 meters. This is uncertainty in position. Remember to change the units to kg. Here was the kg, we changed it to kg. If the velocity is different, please take into account that as well. I just want to stop here today, and I'll come back again for part P. Thank you. See you soon.